ASMR journey into the heart. Here we will explore the path of the blood and the underlying mechanical activity. It's best if you listen to the first part first, but if you haven't, that's absolutely fine. Relax with my whisper. I will explain everything in detail, so you will still understand, although I won't go over the explanation already given in the first part. Take a comfortable position, let your shoulders soften, and listen. If you've already seen the first part, now you're able to vividly picture the heart and its architecture. If not, just look at the drawing before you. We will delve into the familiar terms of systole and diastole, and I'll also explain what is the cardiac cycle. Why do I speak about the cardiac cycle? Well, it's because the heart repeats this sequence in an endless loop, with neither holidays nor rest days, sustaining life in perpetual motion. The heart operates on two intertwined levels, the electrical one and the mechanical one. The electrical level is governed by the conduction system, which generates and propagates the impulses needed to synchronize the contraction of cardiac fibers. The mechanical level involves the myocardium's contraction, which drive the opening and closing of the valves and the subsequent ejection of blood into the pulmonary and systemic circulations. Let's trace together the path of the blood. It's wholly guided by the mechanical action. The cardiac cycle unfolds in two principal phases: diastole, the filling phase, and systole, during which the heart contracts to eject blood. Thus, diastole is synonymous with relaxation and filling. Systole denotes contraction and ejection. During ventricular diastole, the ventricles relax, intraventricular pressure falls, and the atrioventricular valves part, and this will allow blood to flow from the atria into the ventricles. Next comes the atrial systole, a brief atrial kick that delivers a final bolus of blood to optimize ventricular filling. Bolus means just a quantity, final quantity of blood. When ventricular pressure then exceeds atrial pressure, the atrioventricular valves snap shut, and it produces the first heart sound called S1. It helps to imagine these valves as a one-way door between two rooms. The first room, a bedroom, represents the atrium, and the second room, a living room, represents the ventricle. The door opens only from the bedroom into the living room, just as the atrioventricular valves open only towards the ventricles. If you stand in the living room and push on that door, it simply closes. Likewise, when pressure builds in the ventricle and pushes against the valve, it slams shut. It's the S1 sound, and this closing is preventing any backflow into the atrium. There are other mechanisms, but I won't explain them. It works the same way in the heart. When ventricular pressure rises sharply, blood cannot escape back into the atria because the atrioventricular valves are shut. It can only be ejected through the aortic or pulmonary valves. Now that this is clear, let's proceed. Next comes the isovolumetric ventricular systole. Here, the myocardium contracts, driving intraventricular pressure even higher, and yet the volume of blood within remains unchanged because all the valves are closed. That's why we are talking about isovolumetric ventricular systole, because isovolumetric means the volume doesn't change during this phase. Not the whole phase, but during a certain moment. Pressure climbs until it reaches the threshold needed to pop open the semilunar valves and propel blood into both pulmonary and systemic circulations. Semilunar valves are the aortic one and the pulmonary one. Desoxygenated blood flows to the lungs to replenish its oxygen, while freshly oxygenated blood courses forth to irrigate muscles, the brain, kidneys, and the other organs. And it does so according to their needs. Let's pause now for a while to visualize what has just occurred. Recall the rising pressure in your ventricles, represented by the living room. Imagine now a third room, your kitchen, connected to the living room by a door that opens only from the living room into the kitchen, much like the semilunar valves. Now, picture you and I standing together in the living room. I drew some arrows to represent us. We each push on our respective door at the same time. Mine, the door to the bedroom, simply snaps shut. Yours, the door to the kitchen, swings open and grants you passage. In the same way, as ventricular pressure rises in both chambers, blood is driven out into the aorta and pulmonary artery with no hint of backflow into the atria. At the end of ejection, once the ventricle has finished expelling its blood, it begins to relax. Ventricular pressure then falls below arterial pressure, causing the aortic and pulmonary valves to snap shut, making the second heart sound S2. The ventricle then enters isovolumetric relaxation, and as soon as its pressure drops below that of the atrium, the atrioventricular valves reopen and the cycle begins anew. So here I talked about isovolumetric again. It's the same. It means that the volume doesn't change during this period, this small amount of time. With each heartbeat, the heart ejects blood in pulsatile jets, then relaxes before the next beat. This rhythmic ejection yields a pulsatile flow which, through the arterial compliance, transforms into a steady stream within the smaller arteries and capillaries. Arterial compliance denotes the ability of the aorta and large arteries to distend. It's a property conferred by their abundant elastic fibers. These fibers are embedded on the walls of the vessels, these big vessels. In concrete terms, during systole, the aorta distends, storing a portion of the kinetic energy of the ejected blood. Kinetic energy is the energy that an object possesses because it is moving. In everyday term, the faster something goes, or the heavier it is, the more kinetic energy it has. This phenomenon is known as the Windkessel Effect. What's the Windkessel Effect? It's the fact that large recoils, releasing this stored energy and maintaining sufficient arterial pressure to ensure uninterrupted blood flow. Here's an analogous physical principle to understand better how the aorta slows down and smooths out the blood flow. Imagine leaping and landing upon two different surfaces. On a rigid surface, deceleration is nearly instantaneous, generating a high impact force. On a softer surface, deceleration unfolds over a longer interval, so you have more time. So the same momentum is dissipated more gradually and the shock wave is attenuated. So it hurts less on the legs. Likewise, the elasticity of the aorta smooths out the pulsatile burst of cardiac output, converting intermittent jets into steady arterial stream. You have absorbed many intricate details. Now let's embark in a simplified overview to cement the path of blood in your memory effortlessly. First, locate the superior and inferior vena cava on the diagram or in your mind if the heart's architecture is already clear to you. Found them? Now, find the four pulmonary veins. You have them? Okay, here we go. Desoxygenated blood returns to the right heart via the superior and inferior vena cava, while oxygenated blood returns to the left heart through the four pulmonary veins. The atria fill simultaneously and then contract in unison. Thereafter, blood flows into both ventricles concurrently. The ventricular myocardium and the systole. The pressure rapidly raises until the outflow valves burst open. Finally, that pressure propels desoxygenated blood from the right ventricle into the pulmonary artery for reoxygenation, and it drives oxygenated blood from the left ventricle into the aorta to supply every cell of the body with essential oxygen and nutrients. This second part of our ASMR journey through the heart comes to an end. Follow me for the third part, where we will keep exploring its wonders. Thank you for listening. If you enjoyed this, feel free to share, like and leave a comment. It will really help me a lot. And don't forget to subscribe. If you'd like more videos about the heart once you've explored all the three parts, just let me know. I'd be delighted to share more about this fascinating function. See you next time.